Pleasantly to everyone. Today we're going to discuss Module 2, Unit 3, the subject CE 515E. So in this lecture, we're going to discuss the first part of the unit, which is queuing theory. So in queuing theory, we apply what we call your queuing analysis, which is a way of assessing the impacts or the effects of traffic or the activities by determining the magnitude of the vehicular delay and the extent of the queue propagated. So when we say queue, that's another term for pila. Okay? So in queuing analysis, we now apply models which would be derived from our assumptions of the arrival and departures of vehicles in our road section. So aside from the patterns, we would also consider in determining the models the prevailing queue discipline. So when we say queue discipline, this would now be defined as a parameter that would explain how the vehicles or customers arrive at a service station or a service facility. So under queue discipline, we have 5 different disciplines. The first one is what we call the FIFO, or the first in, first out. Next, we have FILO, or the first in, last out. 0, the served in random order. Priority scheduling, and lastly, we have the processor sharing or the time sharing.
So for your queue discipline, the first one, the FIFO, or the first in, first out, is a discipline wherein customers are served in order of their arrival. So kung ikaw yung una na dumating, ikaw din yung unang masaserve, at pag ikaw yung unang na-serve, ikaw din yung unang aalis doon sa service station o sa service facility ninyo. Okay? So, example of your FIFO would be a prepaid taxi queue at the airport. So, dito, hindi pwedeng mauna yung pangatlong nag-text or nagpa-reserve nung taxi. So, dapat FIFO. Okay, ganun din sa pila ng jeep minsan. Kaya sa groceries, sa isang considering one counter only. So, kung sino yung nasa unahan, siya din dapat yung unang ma-serve. Okay? So, next, we have FILO, your first in, last out. So, in here, the customers will be served in reverse order of entry. So, this would have very little applications for traffic analysis. That's why we usually avoid FILO. So, example of this would be the letters or order forms that would accumulate in a pile for offices. So, binigyan ka ng trabaho, yung una mong nagagawa is kung ano yung pinakahuling pinagawa sa'yo. So, another would be people joining an elevator. So, basically, kung sino yung unang pumasok, dun siya sa pinakadulo, kaya siya labas.
So another example for our queue discipline is the 0 or our service in random order. So in here, it would, from the name itself, it would simply mean that the customers are selected or are served at our station at random. So it's irrespective of what their arrival time is in our station or in the system. So it means even if you are the first one to arrive in the service station, it does not necessarily mean that you will be the first one to be served in the queue or in the system, and less. And then we have your priority service discipline. So in here, there is a category or a group in base of the priority. An example of this one would be in bank transactions, for example, or it could also be applied in the supermarkets, wherein senior citizens will be the first one to be served even if they have arrived at a very later time. So in priority service, the service time, the urgency, or the identifiable characteristics will be considered in forming the priority classes. Okay? So the FIFO rule will be applied within each class. So again, let's go back to our example, yung sa senior citizen. So even if he or she, the senior citizen, arrives at a later time, so let's say there are two who arrive, so kung sino yung unang dumating sa senior citizens, siya naman yung maunang ma-serve. Okay? So, the priority, the service will be based on the priority, and within that priority class, we will follow your FIFO or the first in, first out rule. So these are the examples for your priority services. So VIP treatments and senior citizen lanes. So this would also include pregnant women's PWDs.
So the last example for a queue discipline is the processor sharing or time sharing. So in this kind of discipline, the server is basically switched between all queues for a predefined slice or quantum of time in a round-robin manner. So each queue head is served for that specific time only, and completion of service would not matter in this kind of queue discipline. So this is basically used in order to avoid server time that is killed by customer for external activities. So for example, for processor or time sharing discipline, so nangyayari dito, for example, 5 minutes lang per tao yung service time ng service station ninyo. So kung tapos ka o hindi after 5 minutes, yung nagsuserve sa'yo will now move on to the next customer or the next vehicle. Okay, so basically this is kind of a good queue discipline since the time allocated for a certain customer or a certain vehicle is constant. So, hindi na kakaroon ng delays. So, probable dito that if the next customer or the following customer ends up early, then you could come or go back to the first customer to finish it, or depending on the regulation of the service station or the service area. So in queuing theory, we follow also what we call a queuing system. So in a queuing system, there's basically three principles or three factors that we have to consider. So that will be the input, the service station, and your output. So basically, the input would also be likewise your output. Ang ibig lang sabihin yan, the difference is that for the input, this would be characterized by the arrival pattern by an equation that is given by your arrival distribution. So, gaano karami yung dumadating, gaano karami yung pumupunta doon sa service station ninyo. While the output will be characterized by the departure of the vehicles or customers from the service station. This would now depend on the queue discipline that is provided by the service station. Likewise, it is also dependent on the service mechanism that is offered in your service station. So the service mechanism would basically be defined as the manner that customers would be served at our stations. Service mechanism would be like your queue discipline. Okay? So in the queuing system, in our queuing theory, we follow Kendall's notation. So Kendall's notation would be is the most popularly used notation to describe a queuing system, which is denoted by A, B, C, N, wherein A is the input pattern or the arrival pattern or arrival distribution. B will be the service mechanism or your service pattern. And C will be the number of service station that is catering to your queue or your customers' vehicles, and then N will be the limit of the queue or of the users. Gaano karami yung isi-serve nung letter C ninyo nung service station. So we have different traffic patterns or traffic distribution to take note in our queuing system and queuing analysis. So this would now follow the arrival and departure patterns of the queue. So they may either follow a Markov or M distribution, which is simply a random process or a non-uniform distribution. So ibig sabihin, for a certain period of time, the number of arrivals and departures would vary. While we have deterministic or D, which is a process that would be characterized by regular or constant arrivals or distribution or departure distribution. So it means that for every interval of time, the number of arrivals and the number of departures would be the same. Okay? So deterministic, it would mean regular or constant. Markov or M would mean random or non-uniform. So for models of traffic distribution, we have three models that we follow. The first one is the uniform distribution or under the deterministic pattern, wherein we assume under this model that all vehicles would arrive equally at the same time or they are uniformly spaced. The next model is the Poisson distribution or an example under the non-uniform or Markov pattern, wherein we assume that the vehicles would be arriving at random time. And lastly, we have the negative exponential distribution, which is also a non-uniform distribution and an application of the Poisson distribution. In here, in negative exponential, vehicle arrivals would also imply that a distribution time interval between the arrivals of successive vehicles will be considered. So, from what we have studied in traffic flow, in negative exponential distribution, we are considering also the time headway between your arriving vehicles. So, under Poisson distribution, we now follow the equation that the probability of any number of vehicles arriving is equal now to lambda t raised to n times e minus raised to negative lambda t all over n factorial. So basically, this equation just came from your statistics, which is an equation for Poisson distribution. So hindi naman na ito bago. So it's just from statistics. It's just that the value of n will simply be the number of vehicles that we are considering in our analysis. Okay? So Pn will be the probability that n vehicles would arrive at a time given t. The lambda will be the average vehicle flow or arrival rate, and this will be measured in vehicles per time. T will be the duration of time interval over which the vehicles are counted. Okay? And lastly is your natural base logarithm number, which is basically equal to 2.718. So kung may calculator kayo, you can simply use E. If you do not have a calculator, you can use diretso 2.718, which is just an approximation number of E. So in your quizzes or exam, it's better to use the whole value of your natural base. So next we have the negative exponential distribution, which is an application of the Poisson distribution. So we'll just follow the same equation. It's just that we are assuming that n initially is equal to 0. So in that case, we'll have now the probability of 0 vehicles arriving will be equivalent to the probability of the vehicles arriving at a time greater than or equal to the allocated time. So, applying now our equation and substituting n with 0, we'll now arrive at an equation of t is equal to t raised to negative lambda t divided by 3,600. So take note that the 3,600 here is simply a conversion factor for our time. So if the time now is in hours, then you have to divide it in 3,600 so that the value of t will be equivalent or will be in terms of seconds. So note that the term probability for h greater than or equal to t is also known as the distribution of our headways. Okay? So to understand our models, let us solve some examples. So an observer counts 360 vehicles per hour at a highway and assume that the arrival is Poisson distributed. Estimate the probability of having n equal to 0, 1, 2, 3, and 5 or more vehicles arriving over a 20-second time interval. So since it's given already that it's a Poisson distribution, therefore, we're going to use our general equation for Poisson. So in this case, we are given your lambda, which is our average arrival time or arrival rate, and that is equal to 360. And we are given the time interval of 20 seconds. So in here, we can now compute for lambda t, which is 360 vehicles per hour, and then we convert it to seconds, so we could multiply it to the time 20. So basically, the arrival now of vehicles per 20 seconds would be at average 2 vehicles. So this is lambda t. So in this case, what we will do is to substitute now lambda t in our equation for every value of n. So we have computed a while ago, yt is equal to 2 vehicles. So what we want to do is to determine now the probabilities for each value of n. So we'll just be applying Poisson's equation. So the probability for an n value is equal to lambda t raised to n multiplied to e raised to negative lambda t all over n factorial. So what we will do here is to first substitute the values of n and compute for its probability for each value. So if we substitute 0 to the equation and with lambda t equal to 2, so we'll get now a value of 0.135. For n equal to 1, we'll arrive at 0.2707. N equal to 2 is 0.2707. 3 is 0.1804. 4 is 0.0904. And for the remaining value, for n equal to or greater than 5, we'll just simply solve this by subtracting now the sum of all these values, 0, 1, 2, 3, 4, to a probability 1. And that will now be equivalent to 1 minus 0.947, giving us a value of 0.0530. So meaning there is only a 5.3 probability that in 20 seconds there will be 5 or more vehicles arriving in our area. So from this computed values, we could now draw our histogram from our statistics. So we'll just simply draw this based on their values. So this would simply mean that for zero vehicles, we have a probability of 0.135. So it means there's a 13.5% chance that there are no vehicles arriving in 20 seconds. And then we have 0.2707. So same for 0.2707. So it means that there's 27.07% probability or chance that there is one vehicle that will arrive in 20 seconds, or the same probability of two vehicles arriving in 20 seconds. So for 3, that is 0.1804, and 4 is 0.0904. And lastly, if we have 5 or more, that is 0.0530. So as you can observe, the highest probability would be at n equal to 1 and n equal to 2. And the lowest probability that there is an n arriving will be at n which is greater than or equal to 5 vehicles.
So next example, so from the previous problem, what is the probability that the gap between successive vehicles will be less than 8 seconds? And what is the probability that the gap will be between 8 and 10 seconds? So before we start with our solution, let us first identify the difference between the first problem and this problem. So in the previous problem, we were given already a time 20 seconds, which is a definite time in computing for our probabilities for each number of vehicles. For this problem, what we want to solve now is the probabilities of a gap, meaning we are to solve for the form of headway distribution. So there is now time interval between the arrivals of the vehicles. And for letter A, we now have a time headway which is less than 8 seconds. And for B, we now have a range which is between 8 seconds and 10 seconds. So in problem number 2, we now are going to use the equation for a negative exponential distribution. So this is still or an application of the Poisson distribution, except that we are going to use now a value for n which is equivalent to 0. And with that, the probability now that there are 0 vehicles arriving in our range of time is equal to the probability of vehicles arriving at a headway which is greater than or equal to the time given. And in our Poisson distribution equation, we'll simplify it now as E of O is equal to E raised to negative lambda t divided by 3,600. Okay, so for our solution, what we want to do is to represent now the probability of the vehicles arriving with respect to the time. Okay, so in here, we'll be applying now the equation for negative exponential. That is probability of the headway being greater than or equal to the time indicated. And it's equal to negative lambda t divided by 3,600. So t now is equal to 8 seconds. So we'll have lambda t equal to 0.8. Therefore, the probability of the headway being greater than or equal to the time equal to 8 is equal to e raised to negative 0.8, or that is now equal to 0.449. Okay? So, hindi pa ito yung final answer natin because in our problem, what we want to determine is the probability that vehicles would be arriving at a headway less than 8 seconds. So, yung na-solve natin dito is greater than 8 seconds. So, in that case, in order to solve now for the probability of the vehicle arriving at headway less than 8 seconds, that will now be computed simply as 1 minus this value. Okay? So, the probability now less than 8 seconds will be 1 minus 0.449, giving us a value of 0.551 seconds. Okay? So it means that there's a 55.1% chance that there will be vehicles arriving less than within 8 seconds or before 8 seconds. Okay? So letter B, we want to solve now the probability of the vehicles arriving between a range of 8 seconds and 10 seconds. So for our solution, what we want to do here is to subtract the values of the probability that is not included in our range, which is 8 and 10. So meaning, we will now be subtracting the value of your p, which is less than, that is p, when the headway is less than 8, okay? And your probability when h is greater than 10. Okay? So, ang ibig lang sabihin yan, so if we have this line that would represent our time, so this one will be 0 seconds. This one is your 8 seconds, 10 seconds. So, ito more than 10 seconds. So, ang hinahanap lang natin will be this value. Okay? So, from your probability, basically, this value now will have a probability which is equal to 1. So, since ito lang hinahanap natin, I will now be subtracting this value and this one from 1 so that I will be able to arrive at here. So, we have computed already that the probability for vehicles arriving at less than 8 seconds is 0.551. This is 0.551. So, in that case, we will have to solve also for this value. Okay? And that will now be equivalent to 0.368. So, where did this came from? This came from now the equation of E, wherein each is greater than or equal to 10 seconds, and that is equal to e raised to negative lambda t divided by 3600. The only difference is that t here is in 10 seconds. So if you substitute 10 seconds in that equation, you'll arrive at 0.368. So since we have computed already the value for this curve and the value for this curve, we can now compute for this as 1 minus 0.551 minus 0.368 giving us the probability of vehicles arriving within the range of 8 and 10 seconds as equal to 0.081, or it means there's an 8.1% chance that vehicles will be arriving from 8 seconds to 10 seconds. So next example, problem 3. Let's say we are given 900 arrivals in a road section per hour, and 20% of that 900 arrivals will be turning to the left. So determine the probability that 6 or more vehicles would cause blockage upon turning within a time of 1 minute. So what will we do in this problem? So the required here is the probability wherein n is greater than or equal to 6 arriving at time equal to 1 minute or 60 seconds. Okay? So for our solution, we will be using your Poisson's equation or distribution. So lambda can be computed as the arrival rate, 900 per hour. So we convert this to seconds. So divide it by 3,600. And 20% of the arrivals are turning to the left. So we have to multiply it by 0.2. So bakit ang kino-consider lang natin is yung 20%? Kasi yung sa problem, ang hinahanap lang naman natin is yung magkukos ng blockage kapag nag-turn. Okay? So in that case, lambda now is equal to 0.05 vehicles per second. So this we now compute for lambda t, which is 0.05 times the time 60 seconds, giving us 3. So what we will do is to apply now the equation of Poisson. So lambda t, we have computed this one. So ang magvary na lang will be the values of your n. So in that case, we now solve for the values of your probabilities from 0, 1, 2, 3, 4, 5, and greater than 6 or equal to 6. So substituting now, we'll have the probability of n is equal to lambda t is 3 raised to n times e raised to negative 3 all over n factorial. Substitute 0 to this equation, will now arrive at 0.0498. For n equal to 1, the probability will be 0.149. 2, the probability is 224. For n equal to 3, we'll have a probability of 0.224. N is 0.168. N equal to 5 is 0.101. So for the value of n greater than or equal to 1, that will simply be equivalent now to 1 minus the summations of the probabilities for the value of n when it is less than or equal to 5. So in that case, we'll just simply add this up and subtract it to 1. So that will now be equivalent to 0.084. So this is now the probability of the vehicles, of the 20% of the vehicles arriving that would cause blockage. So our queuing system could follow different combinations of patterns or of distributions. So I will give you some examples. The first one is what we call the DD1 queuing system, or as defined by Kendall's notation. The first letter now would represent our arrival pattern. The second letter would represent the departure rate or the service rate, and the number would indicate the number of service station or the number of servers in our system. So the first example, DD1, will have a regular arrival and departure pattern with single or one server with limit equal to 100. So the arrival and departures would be easily represented by straight lines wherein the slope will correspond to their respective flow rates. The next example of queuing system is the MD1, wherein the arrival pattern is a Markov distribution or a Markov pattern, and the departure or the service rate is under a deterministic process. Okay. So for the arrival, the Markov pattern would now follow a negative exponential distribution or random distribution. So for MD1, the equations now will follow that the lambda will be your arrival rate and the mu is your departure rate. So the ratio now of the arrival to the departure is what we call your rho, which is the traffic density or the utilization factor. So when the rho is less than 1, it means that the arrival rate is lesser compared to the departure. So meaning, stable ang flow natin. Kaya ng queuing system, kaya ng service station yung arrival ninyo. Okay? Next, for our formula for MD1, it will now follow the average length of queue will be computed as 2 rho minus rho squared all over 2 times 1 minus rho. And then we have the average waiting time given by the equation omega bar is equal to rho divided by the quantity 2 mu times 1 minus rho, and the average time in the system is T equal to 2 minus rho divided by the quantity 2 mu times 1 minus T. So basically, the average length of queue will be how long are the vehicles na naiipon. Gaano karami yung vehicles na naiipon doon sa queue ninyo o doon sa pila. Yung average waiting time is how long would it take for the vehicle to arrive or to be served at the service station. And the average time in the system will be defined or defines how long is the vehicle inside or inside the system or inside the queue or gaano siya katagal doon sa pila. Okay? So again, average length of queue, gaano karami yung nakapila or yung pumipila. Average waiting time, gaano katagal yung hihintayin bago ma-serve. And average time in the system is gaano siya katagal doon sa buong pila mula pag-arrive niya hanggang sa ma-serve siya. So next, we have MM1, which is the random arrival and departure. So both arrival and departure rates will be at random or non-uniform. So there is a single server and an infinite queue, meaning it can serve any amount of vehicles arriving and leaving. So this is a negative exponential distribution for both the arrival and departure. So for our equations, the average length of queue will be given by this equation. For the average waiting time, it will be this equation. And for the average time in the system will be defined by the equation given here. So for the next example of queuing system, we have MMN, wherein both the arrival and departure or service rates are at random. And we have multiple servers, meaning the server is more than one. So in MMN, we also follow an infinite queue or no limit in the arrivals of our vehicles. So for MMN, we are going to consider only a single queue for the arriving vehicles. And whenever a server or service station is vacant, the next in line will be proceeding to that vacant server. So, to understand MMN, so example, so isang pila lang tayo parang sa accounting nung face-to-face. Pag nagbabayad kayo ng tuition ninyo, isang linya lang yon. Pero madami tayong counters. So kung sino yung nasa harapan, pag nabakante na yung isang counter, siya yung pupunta doon sa counter na vacant. Tapos pag na-vacant yung kabilang counter, yung sumusunod sa kanya naman ang pupunta doon sa second na vacant server or vacant na counter or cashier. Okay, so that's for MMN. So for MMN, we also have our traffic density, which is the ratio of your arrival to the departure. But the rho divided by n will now be our utilization factor, unlike for MM1. Okay? So next, for our equations, for average length of Q, this will now have an equation of m equal to p sub o times rho raised to n plus 1 all over n factorial times n times the quantity 1 all over the quantity 1 minus rho n squared. Okay? So take note, we have here p sub o, which can be computed by this equation. And then for your average waiting time, it will now be given by this equation. And the average time in the system will be given by this equation. Okay? So to understand the different queuing systems, let us solve some examples. So consider now a temporary single lane on-ramp or entrance to an expressway. So while the entrance is open 24 hours, a fixed toll fee is charged from 7 a.m. to 9 a.m. as a form of congestion pricing. So on average, a vehicle now is served for 7.5 seconds, during which the teller receives the fee and gives back the change. So the flow rate now is 600 vehicles per hour during the first 25 minutes, after which it is reduced to 360 vehicles per hour, and this will now remain constant for the next hours. So for our analysis, this will now be a DD1 queue system. So since we are given a constant arrival and constant service rate, and we only have a single service station. So bakit siya DD1? Though we are given two arrival rates, which is 600 and 360, they are still deterministic as they are already established for the first 25 minutes and for the remaining times. So constant siya na 600 VPH for 7 o'clock to 7:25, and constant din siya na 360 VPH after 7:25. Okay? So for our solution, we can now apply these following steps. So firstly, to help us analyze our problem, we could draw a diagram of the accumulated vehicles and the time wherein their slope will now be equal to the flow rate of the vehicles. Okay, so from the diagram that we have illustrated, we can now be able to determine the possible equations that would define the number of vehicles that is arriving and departing. So from our traffic flow discussions, N, which is the number of vehicles, could be computed as the product of the flow rate and the time. So for this problem, the diagram now will look like this one. So it's a linear graph since it is a DD1. So the arrival and departures are deterministic. Okay. So in our graph, we have for the y-axis, it will hold the accumulated vehicles, and the x-axis will be indicating the time. So from 7 a.m. from the problem, the arrival rate is at 600 vehicles per hour until 7:25. So after 7:25, the arrival pattern will now vary and change to a slope of 360 vehicles per hour. So the blue one indicates our arrival, and the purple line will represent our departure or service rate. So from this diagram, we'll now be able to get our equations of the number of vehicles for arrivals and departures. So for arrivals, for the time between 7 a.m. and 7:25, so that is T, which is less than or equal to 25 minutes. So we'll have N will be equivalent to 600 times T. So we convert this to seconds for 2 minutes. So divide VPH by 60. So we'll arrive 10 times T. So this equation is only applicable if the time we are considering is from 7 a.m. to 7:25 a.m. So after 7:25, when the T now is greater than 25 minutes, then the equation will become 360 VPH divided by 60 times T minus T1. And we have to add T times T1. So bakit natin inad yung T 10 times T1? Kasi 'di ba, after 25 minutes, may dumating ng mga sasakyan doon. So ito 'yon. Idadagdag lang natin after 25 minutes yung mga dumadating na sasakyan after 25 minutes. Okay? So that's 10 T1 plus 360 VPH divided by 60 times T minus T1. Wherein T1 now is equal to 25 minutes. So, simplifying, the equation now for the number of vehicles that have arrived after 25 minutes will be equivalent to 100 plus 6T. Okay? So, basically, ang ibig lang sabihin, after 25 minutes, may dumating na 100 or that 250 na sasakyan. And then, after 25 minutes, yung 25 na dumating or 250 na dumating, nadadagdagan siya. And it will be given by this equation. And then, for our departures, since from the problem, it is a constant rate, meaning it is applicable for all values of time. So, from 7 a.m. to any point back to 7 a.m. So, from here, we can use the service rate, which is 7.5 seconds. So, we could now compute it as 8 times T. Okay, so saan galing yung 60? Converted lang siya into minutes, seconds to minutes. Okay, so ibig sabihin, the number of vehicles departing from your service station is given by the equation 8 times T. Okay, so again, for our equations, so for our arrivals, that will be 10T for time less than or equal to 25. And then 40 greater than 25 minutes, that will be given by the equation 160. And for our departure, that will be equivalent to 8. Okay? So from what we have drawn in the diagram, we were able to identify our equations already for the number of vehicles for the arrivals and departure. So from there, we can now solve all our unknowns. So the first one is the time wherein the Q is dissipated or kung kailan mawawala yung pila. And that will happen when the arrival and departure intersects in our diagram. Okay? So, from our diagram, if you could remember, this was the 600. This is the 360 VPH. So this one is our departure. So their intersection would basically be at this point. So in that case, our equation now will be using the arrivals at 360 and the departure at 8t. And when they intersect, when the arrival and departure intersects, it would mean that the number of arrivals will be equal to the number of departures. So when this happens, when the number of vehicles arriving is equal to the number of vehicles leaving, it means that we have already dissipated the queue, or we have cleared our queue. Okay? So from these equations and this diagram, our equation now for the computation of the dissipation will be equal to 100 plus 60 equal to 80. So, ito yung ating equation for the arrival, and this is at 360, or this is after 25 minutes. Okay? So ito yung ating departure naman. Okay, so we have one equation, one unknown, so we'll be able to solve now for the value of time, and that is now equal to 50 minutes. So what does this mean? So after 50 minutes, wala nang pila, wala nang queue na na-form doon sa ating service station. So therefore, the queue now will be dissipated at about 7:50 a.m. Meaning after 7:50 a.m., there will now be no queue formed or expected, since the departure rate after 7:50 will be higher than your arrival rate. So, to prove this statement now, if we are going to review or check our equations with regards to time, so at time less than 25 minutes, so ang arrival natin, our derived equation was at 10 times t. And our departure is equal now to 8t. So let's see, less than 25, let's use time equal to 20 seconds. So the arrival now is equal to 10 times 20, or not 20 seconds, this is 20 minutes. So 10 times 20 minutes, the arrival or number of arrivals will now be equivalent to 200 vehicles. And for our departure, that will now be equivalent to 8 times 20. So that is 160 vehicles. So if we're going to compare the two, the arrival now is greater than our departure. Maraming dumadating kesa sa umaalis, kaya nagkakaroon tayo ng queue. Okay? So if you use 24 minutes, it will be the same. Arrival will still be greater than your departure. And then at 50, arrival is equal to the departure rate. So pag i-check naman natin, at time greater than 50 minutes, so our arrival equation now is equal to 100 plus 60. Departure is still 8t. So let's say after 51 minutes, this will be the t that we are going to use. Our computed arrival now will be equivalent to 100 plus 6 times 51. We have 406 vehicles arriving. And then, for the departure, that will now be 8 times 51, which is 408. So, at 51 minutes, meron ng 406 na dumating. Yung departure natin, merong 408 na umalis na during that time. So, meaning, at a time greater than 50 minutes, our arrival now is lesser than our departure. So, kung mas konti ang dumadating kesa sa umaalis, ibig niyang sabihin, wala na tayong queue, no pila. Okay? So, that's for the time of dissipation. So, the time of dissipation will be given by t equal to 50 minutes. Okay? So, next, we want to solve now for the total number of delayed vehicles. With this, what we are going to do is to simply compute for the delayed vehicles using our departure equation and the time of dissipation. And that will give us 400 vehicles. Okay? So, ibig sabihin, since 50 minutes pa from 7 o'clock bago mag-dissipate, mawala yung pila, so ang total na sasakyan na ipon or parang na-late will be by 400 vehicles. Okay? So next, for the longest queue, gaano kahaba yung pila natin, gaano karaming sasakyan yung na-form, that will now happen at our time equal to 25 seconds. Since mas malaki yung ating arrival rate within the 25 seconds. So in that case, we'll now have the longest queue is equal to the arrival minus our departure at time equal to 25. So longest queue now will be equivalent to 10 times t minus 8t, or in 25 minutes, ang pinakamahabang number or pinakamaraming number ng sasakyan na nasa pila or nakapila is 50. Okay? So for our next required, we want to identify or determine the total vehicular delay. So in solving the total vehicular delay, we could do it by deriving again an equation, or we could simply use the diagram that we have drawn in our previous slide. Okay, so for the total vehicular delay, this will simply be given by the area between our arrival and departure curves. So let's draw again our arrival and departure. So again, we have for the y-axis, that is the accumulated vehicles, the number of vehicles that have been accumulated. And then on the x-axis, we have our time. So we start off with the 7 a.m. So from 7 a.m., we have an arrival rate of 600 vehicles per hour for 25 minutes. So the 250 would come from the equation na 10 times t. Okay? So this is the accumulated vehicles for the time 25 minutes. So after 25 minutes, we have a new arrival rate, which is 360 vehicles per hour. So where did the 25 minutes and the 150 came from? So the 25 minutes came from our equation ng dissipation. So we were able to identify that the dissipation will happen at time equal to 50 minutes. So from 7 a.m. to 7:50 ang ating dissipation, pero meron ng natapos na 25 minutes dito. So yung natitira na lang na time for the 360 arrival rate is 25 minutes. Okay? So from there, the 150 now would simply come from the equation of this slope, which is equal now to 6 times t. And that is equal now to 6 times 25 equal to 150. Okay? So, with that, we can now draw again our departure curve. So, this is our departure curve. That is now. This one now is 80. So, from 7 a.m. to 7:50. So, 8 times 50 will give us 400. So, ito yung accumulated vehicles or yung accumulated vehicles na nakaalis doon sa service station after 50 minutes. Okay? So, pwede din nating isolve yung 150 or yung accumulated vehicles natin, 400, by simply adding 250 na dumating nung 25 minutes and then yung 150 na dumating sa remaining 25 minutes nung 50 natin, nung time of dissipation. Okay? So, either will give us the same value. So, from this diagram now, we'll now be able to solve our vehicular delay. And our equation now will simply be equivalent to so we have now the total vehicular delay will be given by this shaded area. So we have your blue area plus your green area. So blue area now will be equivalent to 1/2 times 25 minutes, 1/2 25 times the time 50 plus 1/2 times 50 plus 25. And that will give us a value of 1,250 vehicles. So, saan nanggaling yung 50? Nanggaling yung 50 na yon is this value. Okay? So, nanggaling siya as 250 minus 200. So, saan nanggaling yung 250, yung 200 na ito? This would come now from our departure equation, 8t. Pero diba, this time is at 25 minutes. So, that is 8 times 25. So, giving us 200. So, this one now is equal to 50. For your equation, that will now be 1/2 of 25 times 50 plus 1/2 of 50 times 25. So, that's for our total vehicular delay. So, next required, we want to solve for the average delay per vehicle. And this will be computed simply by dividing your total vehicular delay by our value of 400. So, the total delayed vehicles. Okay? This will be equivalent to 3.12 minutes per vehicle. So, again, ang average delay per vehicle is the ratio between your total vehicle delay divided by the number of vehicles delay. Okay, so that's for our first problem. We have the next problem. At the exit of a toll gate with single booth, vehicles arrive at random at a rate of 20 vehicles per minute. The service rate is at 22 vehicles per minute. So we now estimate A, the average length of queue, B, the average waiting time of vehicles, and C, the average time spent in the system. So number 2, we are referring with the same service station in problem 1. The only difference is that we now have an arrival which is at random and a service rate or departure rate na constant. So basically, for number 2, our queue system now is under an MD1 queue system since the arrival is Markov or is random, service is deterministic or constant, and we have a single or one server or one station. Okay, so for our solution, we now are given your arrival rate, lambda at 20 VPM, service rate mu is 22 VPM. So in our solution for an MD1 queue system, we want to solve for your rho, which is simply the ratio of the arrival to the departure. This is now equal to 0.901. Though we have a value of rho which is less than 1, but our value is 0.909, which is approaching 1. Therefore, this scenario of MD1 is already starting to become unstable. So, konti na lang, greater than or equal to 1 na yung ating factor. Okay? So, with this, for our required values, we'll just simply use the equations for an MD1. So, for E, the average length of Q, we now use the equation 2 times rho minus rho squared all over 2 times 1 minus rho, which will give us a value of 5.45 vehicles na at average naiipon sa ating system. Next, for B, our average waiting time. So our equation is omega bar is equal to rho all over 2 times your mu divided by or multiplied to 1 minus rho, which will give us 0.227 minutes per vehicle. Or you could also convert this to seconds per vehicle para medyo whole number ng konti yung ating value. Okay, so hindi less than 1 yun. So next, for our letter C, the average time in the system. So your bar T will give us a value of 0.272 minutes per vehicle. So more likely, the average waiting time and the average time in the system is almost similar to each other. Okay? So average waiting time, again, is the time that your vehicles would wait so that they will be served from or by the server, and then average time in the system is the time they would spend in the queue or in the propagation of the queue. Okay? So next example, we consider problem number 2, but instead of having a deterministic service rate, we'll use a random service at average 22 vehicles per minute. And this random service will be caused by a variable toll fees. So, anong ibig sabihin nun? So, dati sa number 1, constant ang dating for the first 25, and at the same time, constant din yung dating ng vehicles natin after the 25 minutes or after 7:25. Also, the service rate is constant since the toll fee for each vehicles would be the same. And then in number 2, the arrival rate is random, but the service rate is still deterministic, meaning they will still have the same toll fees for any kind of vehicles. In number 3, na-consider na ngayon na random siya probably because of the variable toll fees, which is caused by the different kinds of vehicles. So, nag-iiba-iba. Iba-iba yung sukle, iba-iba yung bayad ng vehicles ninyo. So, that would cause now the random service. So, in that case, problem number 3 now will become an MM1 queue service or queue system in which our arrival is random, same given in number 2. Departure service is now random, and we have a single booth or single service station. So, MM1. So, we solve also our average queue, your average waiting time, and your average time in the system. So, for that, we would also need to determine or write first our given. So, for your arrival is 20. Our service rate or departure rate is 22 BPM. And for our equations, we'll have a different equation for MM1. So, for the average length of queue, that is now equal to lambda squared divided by mu divided by the quantity 22, which is mu minus lambda, giving us a value of 9.09 vehicles. And then we have B, the average waiting time. That will now be lambda divided by mu times the difference between your arrival and departure. So the average waiting time will now be 0.45 minutes per vehicles. Okay. So next, we have your average time in the system. So bar T is now equal to 0.5 minutes per vehicle. So, kung papansinin natin yung values ng average queue, length ng queue, the time, waiting time, and our time in the system, and compare it now to the values that we have computed in an MD1 queue system, we could now say that an MM1 will most likely observe a value twice as our MD1 system. So, ibig sabihin, mas mabagal pa rin or mas mahaba yung ating naiipong vehicles for MM1 since both arrival and departures will be at random. Unlike for upper MD1, which has a stochastic service rate, meaning only one is at random and the other one is constant. Okay? So basically, kung papipiliin ako, anong mas gusto ko, then I'll probably use or consider MD1 since mas konti yung naiipong sasakyan, yung pumipila sa ating service station at mas mababa din yung kanyang service or yung kanyang waiting time. So, hindi ako masyadong magtatagal doon sa system ninyo. Okay? So, next problem, we have if the operator of the toll in the previous problems would want now to improve the current condition of the service station or of the toll station, we now determine the queue characteristics if the number of tolls will be increased to 2. So in this situation, we'll now analyze our queue system as an MMN queue system. So it will still be random for both arrival and departure, but will now be increasing our service station. Okay? So, pag dinamihan ko ba yung ating service station, yung toll gates ko, gaganda ba yung flow natin? So, in that case, to determine now the conditions and if it is realistic to increase to 2 or if increasing the tolls by 2 will improve the system, then what we have to do is to again solve for our average values. So for our solution, again, we are going to use our arrival rate, departure rate, and we have computed for your rho, which is 0.909. And for an MMNQ system, we would also need our rho over n. And n now here is given at 2. So for rho over n, we'll now have a value of 0.454. So we apply this in our average length of Q. So before that, we have to solve our P sub O. So substituting now our values of rho and rho over n, we now get P sub O, which is equal to 0.375. Okay? So from there, we can now solve for our average length, which is equal to 0.236 vehicles. For your average waiting time, substitute again the value in our equation. So we'll be able to get a value of 0.12 minutes per vehicle. So that's how long the vehicle would wait for its turn. Letter C, the average time in the system would now be equivalent to 0.057 minutes per vehicle. So from this, we could see that there was really an improvement. So increasing the number of the toll stations will be a good decision since it will be improving our flow. Kasi mas konti na lang yung sasakyan na naiipon ng service natin. Okay? So, that's it for queuing theory. So, for your references, you can check the book of Ricardo Sigua or the following sites. Thank you for listening. So to start off our discussion, we define now shockwave theory. So shockwave theory is basically a principle that we use to analyze long queues that would usually be extending several kilometers or miles. And these queues now would be resulting from temporal or temporary activities. And these activities would basically reduce the capacity of our roadway. So in reality, you experience these scenarios. So, di ba, pag traffic, nag-iipon yung mga sasakyan, and pag naipon yung sasakyan, usually, hindi nakakapag-overtake yung mga nasa likod. So, ibig sabihin, kumukonte yung kaya ng roadway na hawakang sasakyan kasi hindi na umuusad yung ating flow. Okay? So these temporal activities now that we have mentioned in the definition of shockwave theory would now include, one is your stalled vehicles, yung mga nasiraang sasakyan. Another one is parades, pag fiesta, campaign periods. So pag may parada, usually nahihinto yung flow ng traffic. At pag nahinto yung flow ng traffic, there is now a formation of long queues. Okay? So, aside from that, in shockwave theories, the queues formed because of these temporal activities could only be dissipated once that the obstruction or the cause, the activities have already been removed. Okay? So as long as that obstruction, the temporal activity is still present on the road section, you will still have formation of the queues. So in our analysis of shockwave theory, we now use what we call the shock wave. So this is where we have named this principle or this theory. So a shock wave means the motion or the propagation of the change in density and flow of your vehicles. So in shockwave theory, what we are considering is not the speed of the vehicles, but instead the change in the density and the flow rate of our vehicles. So likewise, in shockwave, we now consider this at oversaturated bottlenecks, which are defined as positions or locations in our road sections wherein the traffic conditions would change over space and time. Okay? So what does this mean? It means that the traffic flow, the traffic conditions, your speed, your density, and your flow rate would change over a section of the road with respect to time. Also, the shock wave now will basically be the boundary or will be found at the boundary between your traffic regions. So what are these traffic regions? This would now be the region wherein we have the usual traffic, okay? And then the other boundary would be the region wherein we have the obstruction. So we'll later understand where to locate the shockwave. Okay? So aside from this, shockwaves now could be considered mild. That is, if the platoon of high-speed vehicles would be able to catch up to the platoon of your slower vehicles. Ibig sabihin, mild lang yung shockwave natin, mild lang yung pagkaka-formation ng queue if yung mga nasa huling parte ng road section ninyo, yung nasa hulihan ng mga obstruction, is kayang humabol doon sa ating cause ng queue formation. So it's either mild or significant in our analysis. Significant meaning your free-flowing vehicles that is approaching the queue or the cause of the queue that cannot catch up, thus they are stopped o kaya masyadong mabagal na yung kanilang galaw. Okay? So mild, again, kayang habulin yung cause ng formation. Significant kasi yung nasa likod nung cause ng formation hindi na nakakagalaw. Hindi na nag-move forward. So speaking of shockwaves, we have two types of shockwaves. And the types of shockwaves would now be dependent on the direction of the shockwave with respect to the flow of traffic. Okay? So for the first type, let us consider this section of or these vehicles which represents now region A, which is let's say, the initial or the normal flow of traffic. And then, from here, a new or from their movement, a new vehicle or an obstruction will be approached by this section. So, pag na-approach nung section A, yung obstruction natin, what will happen? Basically, babagal sila. Tama? So, ang mangyayari ngayon, may darating na mga susunod na vehicles which are already moving at the usual or normal flow. So, remember, these green rectangles would represent the vehicles that have changed already their traffic conditions because of our obstructions. So, ito yung mga nagmo-move sa usual or normal natin. That is B. So, we already have two regions. Okay? So, the two regions are defined by the slower section and the faster section or the faster region. So, what happens now? As they move along to this direction, we now have the shock wave being placed at the very end of the last vehicle in our region or section of the slower region. So, what happens? So, kung masyadong mabagal ito, anong mangyayari? Yung mga sasakyan dito, magka-catch up ngayon doon sa ating road section. And while they are catching up, what happens? The shock wave is also moving. So, ibig sabihin, nagka-catch up yung ating mga mabibilis na sasakyan doon sa slower region, thus, naa-adapt nila yung yung bagong traffic condition that is caused by the obstruction. This kind of shock wave now will be what we call a backward propagation or backward shock wave. Why? Because the shock wave now would be traveling upstream against your traffic. So it's moving pabalik or opposite the traffic flow. Okay? So, ito yung initial natin. And then, while we are moving, nagmo-move back yung ating shock wave while the other vehicles are moving or are being parang absorbed by the shock wave or by the new traffic condition. So, that's for backward propagation. So, for the next type of shock wave, we again consider a road section that will be moving at the normal or usual speed or traffic condition. So, as it moves, let's say, to the right, so as it moves, it will now be able to approach an obstruction that would cause it to slow down. And thus, when it slows down, it will now form queues. And the queues now will be coming from the vehicles that will be found on the second region wherein there is still the usual or normal traffic conditions. Okay? So in here, we have our traffic flow to the right. So the shock wave is at the end of our initial slower region. So this shock wave is what we call a forward propagation or forward propagating if the shock wave will be traveling in the same direction as your traffic flow. So, paano yon? So, ito yung ating unang mga vehicles. So, they're moving to the right. So, we have the other vehicles that would be approaching as well towards the right from the second region B, which is the normal flow. So, what will happen now is that the first vehicle in front, so the vehicle in front of region B will now be able to catch up with region A. And as the vehicle from region B catches up with A, our shockwave is also moving at the same time towards the direction of the traffic flow. So parang nagsasabay pa rin silang mag-move. Yun nga lang nakakahabol yung mga sasakyan from section B or region B. Okay? Unlike doon sa backward propagating, naa-absorb ng shockwave yung vehicles from region B simply because the vehicles in region A is slower compared to the movement of the shockwave and the speed or the speed of the vehicles in region B. So sa forward propagating dito, yung vehicles natin from section B will be moving relatively faster or konti lang yung difference ng speed nila with region A. That's why yung ating shockwave dito, yung S, is now able to move together with the traffic flow. Okay? So we'll understand better backward and forward propagating once we have solved some problems. So for our shockwave theory, we are now going to use what we call our shockwave equation. So as we have defined in shockwave is simply the boundary between the two regions wherein we have the normal flow and the region wherein the flow has been slowed down or has changed because of our obstruction. So let's say we have here a homogeneous road section. So we have here road section B or region B with traffic conditions defined by the density and the speed. We have A2, U2. Then at this section, we have our region A, which is represented by the traffic conditions K1, U1. So for our shockwave equation, we will now be basing it on the flow of our shockwave. So let's see, the shockwave now is S and it's moving this direction. And the direction of the shockwave will be defined by U sub W. So we'll have now S, the shockwave. We have defined the boundary between the region A and B, the region between the slower traffic and the normal or faster traffic. U sub W is our speed of the shockwave, represented by the S line. So we'll have a negative value if your density at the capacity or at the slower section is greater compared to that of the density of the first region, region A. Okay? So negative siya if density of the slower region is greater than the density of the faster region. And inversely, if the volume now of region A is greater than the volume of region 2. So this one now is for backward forming shock waves. So if you have a backward forming shock wave, your U sub W will automatically be a negative value. And then we'll have a positive value for the shock wave speed if our formation of shock wave is forward forming or a forward recovery. So, in this sense, pag forward ng ating formation, then K2 now will be greater than or K1 will be greater than K2 and Q1 will be less than Q2. Okay, so you have to take note already of what kind of shock wave is being formed to identify if your U sub W is negative or positive. Okay? So next, we have U1 and U2 will be our space mean speed for regions A and B respectively. And from here, we'll now be relating our motion or the speeds of vehicles in region A and B with respect to our shock wave speed, which is represented now by U sub R. So in relation to the shock wave, U sub R now can be computed as U1 minus U sub W for relative speed at region A, and then for region 2, that will now be U2 minus U sub W. So yun lang yung tandaan natin. Pag relative speed, that will be your space mean speed of the vehicles in the region minus the speed of our shockwave. So from here,